One of the questions that we get quite a bit at B.PUBLIC is really what goes into the design of a high performance thermal envelope. And of course, there's a lot of fascinating factors that go into it, but I really wanted to cover just one today. And just to quickly go over, the thermal envelope for a house is really the envelope or the structure that isolates the interior occupants from the exterior ambient weather, whether it be cold or hot. So really one of the most important factors for thermal envelope design is a higher R value or resistance. And so it just increased insulation for the most part. But there's a lot of factors in design that can significantly impact the actual performance of your R value that you're installing in a wall. And so we wanted to go over that. One is, so again, like having our thermal envelope have a relatively deep cavity. B.PUBLIC uses all natural fiber based insulation. So cellulose is our primary insulation. And like most natural fibers, it has an R value of around 3.5 per inch. So B.PUBLIC's assemblies range from a 9.5 inch thermal cavity to a 14-inch thermal cavity. And so, but there's the factors that really, if you're installing, say, an R50 into a wall, you really want to make sure that your actual performance is an R50. And so eliminating thermal bridges is one of the key aspects for that. And so it's, say if we have a wall, little section right here, typically you would have studs that run all the way through your entire assembly. And so you have energy being able to move through your wall just through that anomaly. And if you look at the studs that are used in B.PUBLIC's assemblies, so they're these eye studs like this. So it's a fully engineered product and it's a 3/8 inch web at this point. So what happens then is the energy, say from the inside, has to pinch down through that smaller web right there. And so there's almost no thermal bridging occurring at that section. So that means any insulation that we put into this cavity from a thermal bridging perspective, we're reaping 100% of its performance. Another really important impact in maintaining full performance of your R value actually has to do with airflow or convection through the assembly. So I'm going to say this is outside and this is inside. If I have a cavity say where my insulation is and air is able to freely move through it, then cold air will come into it and it'll rise through convection or the stack effect, and then it'll cool again and circulate. So it's starting to circulate like this, so it's moving energy more freely within the assembly, and that can also really diminish your overall performance. Incidentally, like fiberglass has a huge capacity for airflow through it, and it's one of the reasons why it's virtually impossible to get, not virtually impossible, it's extremely difficult to get a high performance thermal envelope done using fiberglass insulation unless you really jump through some hoops regarding captive airspaces. So one of the benefits of cellulose insulation is a really relatively high density, and convection is really limited within it. So the air is not able to move from the top to the bottom or from the inside to the out, from the inside to the exterior. And so it's eliminating convection within that thermal envelope. So those really three factors: the higher R value period, eliminating of thermal bridging, and then eliminating convection opportunities within the individual cavities themselves. Those are all three really important basic requirements for the high performance thermal envelope design.